Forking threads. In Haskell, the control.concurrent module provides the ability to create new threads of execution using the fork.io function. When you fork a thread, the runtime system creates a new lightweight thread that runs concurrently with the main thread. This can be useful to perform background tasks or to take advantage of multi-core processors. The threads are managed by the Haskell runtime system, not the operating system, making thread creation relatively cheap. In the code provided, we start by importing the control.concurrent module, which is necessary for using concurrency features in Haskell. In the main function, we use the fork.io function to create a new thread. The first argument to fork.io is an IO action, put_stren. This is executed in a separate thread, which will be executed in the new thread. Meanwhile, the main thread continues executing the next line of code, printing out "this is executed in the main thread" to the console. It's important to note that the program may terminate before the forked thread has a chance to run, especially if the main thread finishes quickly. MVar for shared state. In Haskell, MVar is a synchronization primitive that can be thought of as a box that is either empty or contains a value. It provides a way to safely share mutable state between concurrent threads. When a thread tries to take a value from an empty MVar, it blocks until a value is put into it. Similarly, if a thread tries to put a value into a full MVar, it blocks until the MVar is emptied. In the given code, we import the necessary concurrency primitives from control.concurrent. In main, we create a new empty MVar with the function newEmptyMVar. We then fork a new thread using fork.io. Inside the new thread, we use put_MVar to place a string in the MVar. Meanwhile, the main thread attempts to take a value from the MVar using takeMVar. The main thread will block until the new thread puts the string into the MVar. After the main thread takes the value, it prints it using put_strlen. Software Transactional Memory, STM. Haskell's Software Transactional Memory, STM, provides a composable, transactional memory model for handling concurrent operations, inspired by the transaction concept from database systems. STM transactions can automatically keep track of read and write operations on shared memory and guarantee atomicity and isolation, meaning either all the updates in the transaction are committed or none are, and transactions see a consistent view of memory. The code example illustrates the use of STM in Haskell to safely increment the value of a shared counter. New TVAR initializes a transactional variable. Read TVR and write TVAR are used to read from and write to the TVR, respectively. All operations that should be atomic and isolated are wrapped in the atomically block. Reading the updated value from the TVAR and printing it occurs outside of an atomic block, which is acceptable for a single operation. Asynchronous exceptions. In Haskell, asynchronous exceptions allow one thread to interrupt another thread's execution. This can be important for dealing with timeouts, user interrupts, or other events where you want a thread to stop what it's doing and handle an exception. This can be tricky because the exception can arrive at almost any point in the target thread's execution. In this code snippet, we fork a new thread using fork.io, and this child thread simulates some work by printing messages and pausing. The main thread waits for 2 seconds using thread delay, then sends an asynchronous exception, user interrupt, to the child thread using throw_to. The child thread, if not dealing with the asynchronous exception, would simply print working and still working at 1-second intervals, and finally done working. Asynchronous exceptions can happen at any time and require careful handling. Otherwise, they can cause unpredictable behavior in your program. Concurrent data structures. In Haskell, concurrent data structures are those that are designed to be safely accessed and modified by multiple threads simultaneously. One of the common concurrent data structures is the MVar, a mutable location that can be empty or contain a value, providing a way for threads to communicate and synchronize. Let's look at a simple example using MVar. This code demonstrates the use of an MVar in a concurrent Haskell program. It imports necessary functions from control.concurrent.mvar and control.concurrent. First, we create an empty MVar using newEmptyMVar. Then we spawn one thread that puts a character X into the MVar. The second thread, initiated with a thread delay to simulate asynchronous behavior, takes the value from the MVar and prints it. Finally, the main thread waits to ensure that the second thread has time to complete its action before the program terminates. Parallel strategies. In Haskell, parallel strategies provide a high-level abstraction for parallel computing. They allow you to define how a computation should be evaluated in parallel without manually managing threads. The control.parallel strategies module defines the strategy type and functions for common parallel patterns. We'll demonstrate using strategies to evaluate a list of values in parallel. In the code provided, we first import the control.parallel strategies module, which includes the parallel strategies functionality. The function parMapStrategy takes a function f and a list xs, then applies f to each element of xs in parallel. This is achieved using the using function, which applies a strategy to a computation. Here, we use the parList strategy with the rDeepSeek reducer, which means that each element of the list is evaluated fully in parallel to avoid lazy evaluation issues. Finally, in main, we apply parMapStrategy to the doubling function stus2 and a list of numbers from 1 to 10, and the results are printed out. Deterministic parallelism. Deterministic parallelism refers to the type of parallel computation where the result of the computation is guaranteed to be the same, regardless of the timing of the parallel execution. This contrasts with non-deterministic parallelism, where results can vary due to race conditions or other timing-related phenomena. In Haskell, deterministic parallelism can be achieved with libraries such as control.parallel strategies, which allows us to use evaluation strategies to control the parallel evaluation of expressions. In this code snippet, the parMapReduce function leverages deterministic parallelism to concurrently map a function over a list and then reduce it. It uses parMap from the control.parallel strategies library, which applies a mapping function to each element of a list in parallel. The rDeepSeek strategy is used to ensure that each mapped value is fully evaluated to avoid lazy evaluation gotchas. The reduce func combines all the elements of the list to produce a final result. Here, we calculate the sum of the squares of the numbers 1 through 10 in parallel, and then sum the results. The resulting sum of squares is deterministic and will always yield the same result, because plus and 2 are pure functions, and parMap ensures that the parallelism does not affect the final value. Sparks and the Eval monad. In Haskell, sparks are a lightweight way to express potential parallelism. Unlike threads, sparks do not run on their own. Instead, the runtime decides whether to execute a spark in parallel. The Eval monad is a tool for describing parallel computations that produce sparks. Here's a simple example using the Eval monad from the control.parallel.strategies library, which shows how to create and run parallel computations. In this code, parMapReduce is a function that performs a map operation in parallel using parMap, then reduces the results using foldm. The Eval monad, together with the rpar strategy, is used to describe which parts of the computation can be performed in parallel. The rpar function creates a spark for an expression. The evaluation strategy rpar does not guarantee that the computation is performed in concomitantly, but it suggests to the runtime that it may be beneficial to do so. The parMap function is a parallel version of the standard map, automatically creating sparks for each application of the mapping function. The foldm function combines the mapped results using the provided reduction function. This example demonstrates how Haskell allows programmers to express potential parallelism without directly managing threads. Using GHCi debugger. The GHCi debugger is a tool that allows you to observe the execution of your Haskell program, set breakpoints, and inspect values. It can help you understand program behavior and identify bugs. First, set fbbreak on exception configures GHCi to stop at the moment an exception occurs. The break5 command sets a breakpoint at line 5 of your program. When you run trace main, GHCi begins execution of main and stops at the breakpoint, allowing you to inspect the program state at that point. The history command shows the sequence of function calls that led to the current point in the program. With step, you can step through the execution of the program line by line. Property-based testing with QuickCheck. Property-based testing is a technique where we verify that a certain property holds for a large set of possible inputs, rather than checking individual cases. QuickCheck is a Haskell library that automates property-based testing by generating random inputs and checking whether the property is true for all of them. This helps in identifying edge cases that are often missed during manual testing. In the given code, we import the QuickCheck library and define a property prop reverse twice, which checks that reversing a list twice will give us the original list back. This property should hold for all lists of integers. We then use QuickCheck prop reverse twice in the main function to test this property. QuickCheck will generate random lists of integers and check if the property holds for each of them, reporting any failures. Unit testing with HUnit. HUnit is a unit testing framework for Haskell, allowing you to create and run tests for your functions to ensure they behave as expected. Using HUnit, you write test cases, group them into test lists, and run these to check the results against expected outcomes. Below is an example of how to create a simple unit test for a function that adds two numbers together. The code starts by importing the test.unit module. We define a simple addition function, add, that takes two integers and returns their sum. We then write a test case, test1, which uses assert equal to specify the expected result 3 for the expression add1 2. In the main function, we run test1 using runTestTT. If the test passes, runTestTT will report that everything is okay. If it fails, it will report the difference between the expected and actual result. Code coverage with HPC. Haskell Program Coverage, HPC, is a tool for tracking code coverage of Haskell programs. It shows which parts of your code are being exercised by tests, which can help identify untested parts. To use HPC, compile your program with the nachfhpc flag, then run your tests. This code snippet demonstrates how to compile a Haskell program with coverage tracking, execute it with some test input, and generate a coverage report. The GHCi.fhpc command compiles myprogram.hs with coverage instrumentation. After running the program with test input, HPC report generates a coverage report, whilst excludical main omits the main module from the report, which is common if you don't want to track coverage in the application's entry point. Profiling with GHCi. In Haskell, profiling is a technique used to measure the performance of a program. GHCi, the interactive environment for GHC, Glasgow Haskell compiler, can be used for profiling to identify bottlenecks in a program. The following illustrates how to enable profiling in GHCi and view a simple profile report. In the GHCi session, set+s enables time and memory statistics. Then, a recursive Fibonacci function fib is defined. The main function computes the 30th Fibonacci number and prints it. After the computation, set-s disables the statistics. Running this will show the time taken and memory used for the computation, providing insights into the performance of the fib function. Benchmarking with Criterion. Criterion is a powerful library in Haskell used for performance measurement. It allows for accurate benchmarking by taking into account statistical noise, and it's easy to use. To benchmark with Criterion, you need to include it in your project, import necessary modules, and then define benchmarks. The typical Criterion benchmarking workflow involves setting up a Criterion function that runs benchmarks comparison. The provided code imports the Criterion library with import criterion.main and defines a naive Fibonacci function fib. The main function sets up the benchmarks using default main, which automatically handles the command line interface for running benchmarks. It includes a benchmark group, bgroup, named fib, with 3 benchmarks, representing the time it takes to compute Fibonacci of 10, 35, and 37. The WHNF, weak head normal form, function is used to force the computation of the fib function to a single result without fully evaluating it, which is good enough for benchmarking purposes. Tracing and logging. In Haskell, tracing and logging can be done using the debug.trace module, which provides functions that allow you to print messages to the console for debugging purposes without changing the behavior of the program. One such function is trace, which can be used to output the values of expressions during evaluation. This can be incredibly useful for understanding the flow of execution and for pinpointing where things might be going wrong in the code. In this code example, we import the debug.trace module and define a function to compute Fibonacci numbers. We use the trace function to output a message each time Fibonacci is called. The trace function takes two arguments, a string to print and an expression whose value will be the result of the call. The messages help us understand the call pattern of Fibonacci and can highlight inefficiencies, such as repeated calculations in this naive recursive implementation. Programming idioms. In Haskell, map and filter are commonly used idioms for list transformations. Map applies a function to every element of a list, whereas filter selects elements of a list that satisfy a predicate. The provided Haskell code defines a function doubled evens that takes a list of numbers and first filters out the odd ones, then doubles the remaining even numbers. It uses function composition with the operator to connect filter even and map to, creating a pipeline of operations that is applied to numbers. Effective library usage. Before using a library, it is fundamental to understand its documentation. Haskell libraries are typically documented on Hackage with type signatures, brief explanations, and sometimes examples. Documentation can be found on the Hackage package page for the library. Start with the library's synopsis and description, then look through the module exports to find functions and types you're interested in. Pay close attention to the function type signatures, as they are a concise description of what the function does. HUnit comments often provide useful insights, and source links can be valuable if the documentation is sparse. Performance considerations. Haskell functions can have different time complexities depending on how they are implemented. Understanding time complexity is crucial to writing efficient Haskell code, especially knowing the difference between O1 and ON operations. The provided fib function calculates the nth Fibonacci number. Instead of the naive recursive approach, which is O2 to n, this implementation uses a tail recursive helper function with an accumulator, achieving linear time complexity, or ON. Since Haskell supports tail call optimization, the tail recursive version is also space efficient. Writing idiomatic Haskell code. Idiomatic Haskell refers to the style and conventions that are commonly agreed upon by the Haskell community. It encompasses not only things like syntax and naming, but also the use of certain idioms and patterns that make code more readable, maintainable, and performant. Let's go through an example of how to write idiomatic Haskell code. In this code snippet, doublelist is a function demonstrating the use of higher-order functions, which is a common and idiomatic practice in Haskell. Higher-order functions like map are preferred over explicit recursion for simple transformations. Calculate result uses a let expression to bind local variables, which is idiomatic for keeping code clean and readable. Additionally, Haskell idioms prefer immutability and expressions over statements, so let is used over do for simple variable binding, and variables like sum and product are immutable. Web programming with Yesod or Servant. Yesod is a Haskell web framework for creating type-safe, RESTful web applications. It leverages Haskell's strong type system and compile-time checks to ensure the safety and correctness of web applications. The given code is a basic Yesod application. It starts by enabling necessary language extensions and importing the Yesod library. A data type myapp represents the application itself. A memkey Yesod block is used to create Yesod routes. Here, we have a single rote slash that is associated with a handler homeR, which is a GET request. The getHomeR function defines the handler for /route, using default layout to set the document title and body. Lastly, the main function starts the application on port 3000 using the warp server. Database access with persistent. Persistent is a Haskell library for interacting with SQL and NoSQL databases in a type-safe and abstracted manner. It allows developers to define their database schema using Haskell data types. Persistent uses template Haskell to generate code that maps these types to corresponding database tables. The code snippet uses several language extensions necessary for Persistent's template Haskell features. We import modules to work with Persistent and a specific backend, SQLite. Share, along with template Haskell persist lowercase quasi-quota, is used to define a person data model with name and age fields. mkpersist generates corresponding Haskell types and functions based on the model we define, while mkmigrate generates functions for migrations. A main function runs a demo using SQLite, migrates the database to ensure it matches our models, inserts two-person records, and retrieves one using get. System programming. System programming often involves working with the file system to read from or write to files. In this example, we are going to write a Haskell function that creates a file and writes a string to it. The system.io module provides functions for dealing with files. Here, write to file is a function that takes a file path and text as inputs. The openFile function opens a file in write mode. hputster writes the text to the file handle obtained. Finally, hclose closes the file handle. Foreign Function Interface, FFI. The Foreign Function Interface, FFI, in Haskell provides a way to call functions written in other programming languages, like C, directly from Haskell code. This is particularly useful when performance-critical tasks need to be optimized, or when leveraging existing libraries written in other languages. This code demonstrates the basic syntax for importing a C function into Haskell. The foreign import C call syntax declares an external function, followed by the string literal giving the C linkage name. math.hsyn specifies that we're importing the syn function from the C standard library header math.h. The csyn double part defines a Haskell function named csyn that takes a double argument and returns a double. The types must match the expected types of the foreign function. Dependent types. In Haskell, dependent types allow types to be predicated on values. Haskell does not have full support for dependent types as a core feature, but it can emulate some dependent typing features using GHCis, generalized algebraic data types, or by using languages extensions like data kinds and type families. Below is an example using GHCis that simulates a dependent type, ensuring only vectors of the same length can be added together. The code defines a simple implementation of natural numbers nat and a gdt for a vector type vc, which encodes its length in its type. 0 represents the natural number 0, and suc_n represents the successor of a natural number. The vec type is a gdt that distinguishes between an empty vector, nil, and a vector with at least one element, cons. The function vad recursively adds two vectors of the same type level length. The type system enforces that you cannot add vectors of different lengths, as there is no case for adding nil to cons or vice versa. Type-level programming. Type-level programming in Haskell involves working with types as first-class citizens, where you can perform computations and manipulate types much like you would with values. GHC's extensions like data kinds and type families play a crucial role here. We'll demonstrate type-level programming by creating a type-level function that calculates the length of a type-level list. The code snippet uses GHC extensions to define a type-level function length. The function computes the length of a type-level list of natural numbers. It features a recursive type family, which acts similarly to a value-level recursive function. The base case, empty list, yields 0, while the recursive case adds 1 to the result of length called on the tail of the list. These operations are all conducted at the type level, which means that length can be used to compute and enforce lengths of lists at compile time, adding a layer of type safety to Haskell programs. Functional Reactive Programming, FRP. Functional Reactive Programming, FRP, is a paradigm for writing interactive programs using a functional approach. It combines the idea of time-varying values and event streams, allowing for the creation of responsive and resilient UIs, animations, and other time-dependent programming constructs. FRP abstracts away the complex state management and synchronization issues typically associated with interactive applications. In Haskell, libraries like Reactive Banana provide the toolkit to implement FRP. In this snippet, we're demonstrating a simple use of the Reactive Banana library for FRP in Haskell. The code creates an event-driven program that emits a message every time a button is clicked. Firstly, we set up the FRP network within the network description function using the moment.io monad. We then define an event eButton that captures the clicks of a button. Each click is mapped to a string message. bClicks is a behavior that represents the latest string to display. Stepper creates a behavior that changes its value whenever the event occurs. Finally, reactimate turns a behavior into an I/O action, allowing side effects, in this case, printing to the console. Domain-specific languages, DSLs. Domain-specific languages are specialized mini-languages created for a particular domain, such as web development, database interaction, or scientific computation. In Haskell, DSLs can be implemented as libraries using the language's advanced type system and abstraction capabilities, allowing developers to write code that's expressive and close to the domain logic. Here we'll look at a simple DSL for generating HTML. The code snippet defines a simple DSL for representing HTML content. It declares a data type HTML, which represents HTML elements and can either be plain text, bold text, or italicized text. The render.html function recursively transforms our DSL representation into actual HTML by matching patterns and concatenating strings. Finally, sample.html demonstrates how to use our DSL to nest bold and italic elements. The Haskell ecosystem and community. The Haskell ecosystem is a rich and evolving environment influenced by both academic research and industrial application. Key components include the Haskell platform, libraries, tools like Cabal and Stack, and the online package repository Hackage. The community is active, with contributions to open-source Haskell projects, mailing lists, the Haskell Wiki, and online forums like Reddit's Ask Haskell. This code section would typically contain Haskell code if the topic had a specific coding aspect. In this case, since our focus is on the ecosystem and community, which are not code-centric, there isn't a relevant code example to provide. Instead, we understand that the ecosystem encompasses the tools, libraries, and resources available to Haskell programmers, while the community aspect refers to the collective efforts and communication channels through which Haskell developers interact, share knowledge, and collaborate. Current research and trends in Haskell programming. Dependent types are a powerful feature which enable types to be predicated on values, thus allowing for richer type-level computation and ensuring more invariance at compile time. There is ongoing research to integrate dependent types into Haskell, which is manifested in the form of the Dependent Haskell project. The example demonstrates a light version of dependent typing in Haskell using GATs. The vec type is a length-indexed vector, which means its type carries information about its length. The vec_length function computes the length of a vector at the type level, which ensures that vectors cannot be combined incorrectly according to their lengths at compile time without actually needing to compute their lengths. Contributing to GHCi or other Haskell tools. Contributing to GHCi, the Glasgow Haskell compiler, or other Haskell tools requires familiarity with the tool's codebases, understanding of the development process, and knowledge of the programming language itself. Many projects often welcome contributions in several forms, such as bug fixes, feature enhancements, and documentation improvements. To contribute, one typically starts by setting up the development environment, which involves cloning the project's repository, for example, GHCi's GitLab repository. Following this, you may opt to look for good first issues, which are usually marked for newcomers. The actual contribution process then involves creating a fork, making code changes in a branch, and submitting a merge request, MR, or pull request, PR. It is important to follow the project-specific guidelines for coding standards and to include tests and documentation for your changes. Finally, the MRPR will be reviewed by project maintainers who will provide feedback or merge the changes.